Hi everyone, I'm Zishen. Today I'm very glad to present our work, Analyzing and Improving Fault Tolerance of Learning-Based Navigation Systems. This is a collaboration work between Georgia Tech and Harvard University. First, please allow me to briefly introduce myself. I'm a PhD student at Georgia Tech. I have a broad research interest in real-time design, computer architecture, and edge intelligence, with a focus on energy efficient and reliable hardware and system design for autonomous machines. I received my master's degree at Harvard University in 2020 and bachelor degree at Harvard Institute of Technology in 2018. As we know, the learning-based navigation systems are widely used in autonomous applications, which takes the input information and directly generate the output actions. And specialized hardware accelerators have been proposed for the high performance and energy efficiency for such tasks. However, the hardware faults are increasing in systems and can violate the task safety. And traditional redundancy-based protection methods are challenging to deploy on the resource-constrained edge applications. Therefore, the questions we're asking and trying to solve in this paper is how's the fault tolerance of learning-based navigation systems, and how can we detect and mitigate that? So some works have begun to look into this field. Some works evaluate the sensor noise and hardware faults in the traditional kernel-based pipeline. However, the reliabilities of the emerging end-to-end learning-based pipeline has not been adequately explored, which is the focus of our work. And in terms of the fault characterization, the impact of fault in neural network has been studied in the supervised learning, but they didn't consider the inherent resilience of the long-term decision-making capability of the end-to-end learning-based system, which we take the first step to explore. And for fault mitigation techniques, different from the traditional redundancy-based method, represent the application-aware techniques. We are considering the characteristics of the learning-based system. So in this work, we first build a fault injection toolchain, and then conduct a large-scale fault injection study to characterize the system's resilience, and finally propose the cost-effective fault mitigation techniques. So first, a fault injection toolchain for the learning-based systems. We consider two types of the hardware noise in this work, the transient fault and the permanent fault. So the transient faults mainly arise from the external perturbations and may only exist for a short period. Permanent faults usually result from the manufacturing defects and are continuous with time. So we use the widely adopted the random bit flip and the stochastic fault models as abstractions. We consider faults in the memory, which are pertinent to the learning-based system due to its large storage requirement. We do not consider faults in the control logic because the scheduling is failing down by the host CPU. So this fault model is in line with the many previous works as listed here. For fault injection, it is performed in two modes, static and dynamic. The static injection is conducted offline before training or inference, and dynamic injection is conducted during the execution, and overheads are minimized by implementing the fault model as tensor operations. And one thing to note that is faults may greatly impact both the training and inference. So in training, different from conventional offline training and deployment method in supervised learning, the learning-based or the RL-based system usually requires the real-time training and fine-tuning on edge. So faults in training might impact the learning process and even affect the policy convergence. And in inference, the different from the DM models in supervised learning, the RL policy's quality depends on how effective it is in the long-term sequential decision-making. So faults at one stage might propagate to the subsequent stages, suggesting that there are different vulnerabilities to faults than the traditional DM workload. Then we conduct a set of the in-depth fault injection experiments. To understand the fault impact, we start from a small but popular grid word problem. as you can see, the task for agent is navigating from the start cell to the goal without colliding into obstacles. So we test both the neural network-based method and tabular-based method that use a table to store the states and their corresponding actions. And we use the agent's successful rate to evaluate the system performance. Let's see some results. The first is the fault impact on training. We train the 1000 episodes, and x-axis is the which episode the fault gets injected, and y-axis shows the bit rate. So the color-coded is the agent successful rate. The darker, the worse performance. So for transient fault, we can observe that when the bit rate and fault injection episode are introduced beyond a certain threshold, the performance decreases quickly. And for permanent fault, we find that the stuck at 0 has comparable impact as transient fault, indicating that the agent can learn and adapt itself to the permanent fault patterns in training. Another finding is that stuck at 1 has more severe impact than a stuck at 0. So this can be explained from the policy weight distributions. We can see that there are much more 0 bits than 1 bits, and most value is centered around 0 and have very narrow range. So the greater magnitude faulty values aroused from the stuck at 1 have more impacts. We also performed similar experiments on a tabular-based method, and we find that the neural network approach exhibits the higher resilience than to the trained fault. So this is because the neural network training process is not significantly impacted by the trained faults, and it can recover from the faults quickly due to its advanced optimization techniques and the representations. We now ask the following question: whether the policy can finally converge after faults are injected. This can help us further understand the system's long-term learning capabilities on a different type of faults. So for transient faults, we inject the bit flip at 900th episode and measure how long the system needed to converge. We can find that the system can finally achieve convergence. And for permanent fault, we double the training episodes and see whether the successful rate can goes up. But we find the extra training doesn't bring obvious improvement. So this is because a steady low exploration rate impedes the agent learn the permanent fault. And we also experiment on a tabular-based method and get a similar findings. The only difference is the tabular-based methods needs a longer time to converge. And after training, we look into how faults impact the inference. So the inference of the learning-based system is a sequential decision-making process, and the policy will be utilized in each action step based on the current state. So the transient fault may only impact the current single step is the transient 1, or impact the whole executions is transient M. We see that the transient 1 has a negligible effect compared to the transient M. So this is because a single wrong decision doesn't necessarily result in a task failure and can be remedied in the following actions. And for permanent fault, the stuck at 1 has a much severe impact than the stuck at 0 due to the sparsity nature of the neural network parameters. And we also experiment on the tabular-based method and get similar observations. So after getting these insights in the grid word problem, we move to a more complex problem, the drone autonomous navigation. So we use Pedro as a simulation platform, which is powered by the Unreal Engine and AirSim. So during the task, the drone is initialized at a start location and navigate across the environment, avoiding obstacles, and fly as long as it can. So to quantify the performance, we use the average drone flight distance before collision as a metric. So the longer the distance, the better of the performance. And let's look at how faults impact online training process. So the model is first trained offline using the DDQN, and then fine-tuned last 2 layers online using transfer learning. So the trended fault is injected in a single random step during the online training. And we can observe that the fault quality decreases with higher bit error rate and later fault occurrence. So for permanent fault, we observe the stuck at 1 faults have much higher impact than stuck at 0, which is similar as what we saw in the grid word problem. And for inference, first we look into the faults in different locations. So we can see that the input buffer is relatively resilient since image information has some redundancy. And the trended fault in activations with active bring more performance drop than inputs because the activation faulty value will be propagated to all neurons in the next level without any masking. And weights are more sensitive to the trended fault than activations due to its massive reviews in the convolutional layers, which will impact a larger value subset. We also evaluate the resilience of the different layers, so we can find that the first 2 convolutional layers exhibit the higher resilience because the max pooling and review activations here can mask some errors. However, there's no pooling layer after the 3rd convolutional layer, making it more vulnerable. And the second FC layer is the most vulnerable to bit flips because it is the last layer that directly dictates the actions. We also evaluate the resilience of the 3 fixed point data types. We observe that the 4-bit integer type exhibits the higher resilience than other 2. So this is because it has a narrow range and are already able to capture the range of the weights without performance loss. So it is noted that to achieve the higher resilience, the data types should be able to optimally capture the value range rather than pursuing an unnecessary larger range. We then evaluate the resilience of the different bit positions. We find that only sign and high-order integer bits are vulnerable, and the impacts are proportional to their position significance. Last, based on our observations, we propose the cost-effective fault detection and recovery techniques for both the training and inference stages. So for training, we have seen that the faults can bring the low reward. So we use the change in the reward as the fault indicator. For trended fault, if the reward drops exceeds the threshold, it is supposed that a fault is detected. And for permanent fault, after the exploration rate drops to a constant value, if the reward is still lower than 50% of the maximum value, then the permanent fault is supposed to be detected. And to mitigate the fault impact, we propose the dynamic exploration rate adjustment scheme. We know that one of the fundamental trade-offs impacting the RL training is the exploration to exploitation ratio, which determines how agents explore the action space and exploit the knowledge. So if the trended faults are detected, the systems will automatically increase its exploration rate as a function of the fault detected time and reward drop. And if the permanent faults are detected, the system will automatically increase its exploration rate and lower its decreasing speed. We evaluate these techniques by repeating the previous experiment, and we find that almost all trended faults happen before the 800 episodes become benign. And the impact of the permanent fault is also relieved by around 10%. And for inference, we adopt the anomaly detection and use the parameters value range as an indicator to detect outliers. So once the policy is trained, the value ranges will be instrumented and derived, and 10% detection margin will be applied on bound. And to mitigate overhead, the instrument and value comparison is conducted asynchronously. And once an anomaly data is detected, the operations around this data will be skipped. So the intuition is that the sparsity nature of the neural network parameters and the data with small magnitude has a higher possibility to become an outlier after bit flip. So compared to the no mitigation cases, the agent successful rate increased by around 2x in grid work, and drone's flight quality increased by around 40% after the fault mitigation is applied. Moreover, if the runtime overhead is less than 3% without requiring the redundant bit as opposed to ECC. And here are some trajectories we captured during the drone flight. So when there's no fault, the drone continues to navigate and fly in the environment. But after injecting the bit flips, the drone is easier to collide into the obstacles. And after applying the fault mitigation techniques, it can recover from the fault impact. And we have the more results in the paper, and please feel free to refer to our paper. So to summarize in this talk, we discussed analyzing and improving fault tolerance of the learning-based navigation systems. First, we showed the safety and reliability of end-to-end learning-based navigation systems is very important. Second, a fault injection toolchain is implemented to emulate the hardware faults and enable the rapid fault analysis. Third, a large-scale fault injection study is conducted against permanent and transit faults. Finally, the low overhead fault detection and recovery techniques are proposed for both training and inference. Thanks for listening. With that, I will conclude my talk and happy to take any questions.